It's the 21st of March, and this is a summary of analysis of open systems. So we are talking about Chapter 5, and what we've said basically is that for an open system energy analysis, that you always use the first law of thermodynamics in combination with the conservation of mass, and that those two equations can be either used as amounts or rates. The rate, in order for you to rate form the equation, we have to have steady flow systems. But the process is to write both of these equations in their entirety and then cancel out terms as appropriate. For example, here, if you didn't have any mass going out, this entire summation term would cancel out. If you didn't have any work done, you would cancel out the work, and so forth. So the first law and the conservation of mass written for amounts can be found on page 251. This is fairly complete. If there was a change in PE, potential energy, or kinetic energy, we would have to include them in the system. But basically what you can see is that we're separating out the mass that comes in and out of the system and the mass that stays in the system. Okay? Then on the other side of the equation, on the left-hand side, are the types of energy that cross the system boundary without being associated with mass, heat, and work. So we have energy associated with heat and work. We have energy not associated with heat and work, and we have the change of mass in the system. So this speaks to conservation of energy, just energy changing form. At the same time, we need to look at the amount of mass that goes in minus the mass that goes out being equal to the change of mass of the system, which is the mass at time 2 minus the mass at time 1. So this is for example, a uniform flow problem, like if you have a bathtub or any sort of a mixing chamber, anything that is not really a flow-through process, but where you have mass accumulating or discharging from a vessel or an apparatus. All right, now for other problems, we may want to look at rates. And when we talk about rate, we just use I believe it's called Leibniz notation, where you put a dot above some variable, so like x dot is equal to essentially dx dt. So we just use that notation. When we use a dot, we're just talking about the first derivative with respect to time. All right, so once again, the equations here appear on page 251, a little farther up on the right-hand column. But we basically have, it writes that the summation of the mass flow rates in is equal to the mass summation of the mass flow rates out. Now this is if mass amount in the control volume does not change. So in other words, if you don't have, if you have like a turbine or a nozzle or a diffuser where the mass is just passing through any kind of a pipe, for example, I can talk about the mass flow rate in, the mass flow rate out being the summation of those two things being equal to each other because the amount of mass in the vessel remains the same. Now, if it's not the same, you can just kind of gin up this equation and think about it like if you take, let's start from the beginning. If you take the mass at time 1 and you add to it the mass that comes in, and you subtract from that the mass that goes out, that will be equal to the mass at time 2. So if we rewrite this a little bit, we get this, m2 minus m1, which is, of course, delta m in the control volume. And then if this is differentiable, we can say the flow rates, so m dot, dot. When we take the first derivative of this with respect to time, it becomes dmcv dt. Right? And then if we have more than one inlet or more than one outlet, we can make it more general by adding summation signs. So this is really the most general form of the equation. Underneath it, we have a rate equation for the energy for the first law of thermodynamics. Q dot is referred to as the rate of heat transfer. W dot is power. Okay? And if we take a look at that, if we have no mass accumulating within the system, let's put this if dmcv dt is equal to 0, in other words, once again, we're not accumulating mass, then all we have to worry about is the energy that comes in and out associated with mass. So we have the summation on the outlets of the individual mass flow rates times h plus v squared over 2 plus gz of each of those outlet streams minus the summation on the inlet of the same energy variables. Okay? And that is true if dmcv dt is equal to 0. If not, you need to take into account the energy associated with the mass at time 1 and time 2, which that's a very complicated problem, and we really are not going to encounter that in this particular chapter. But if we did, it would basically look like the integral of whatever energy terms times rho times dv within the control volume as we differentiate that integral with respect to time. Okay, so we could add that on to this and have the rate of change of energy within the control volume with respect to time as well. All right, now the introduction of one other variable. Actually, there's two, but one of them is not shown on this page. That's all right, we'll talk about that in just a second. We use the letter theta, and we introduce that as being the total energy of a flowing fluid, or flow energy. And it's per unit mass. So if you see this term, what this really means is, if you go back to this equation, h plus v squared over 2 plus gz is equal to theta, right? So what it's talking about is if a mass is in motion, if you divide out the amount of mass or the mass flow rate, that the energy terms added together per unit mass is equal to theta, right? There's one other term in here they don't introduce on that page, but we talk about non-flow energy as well, which is actually just the sum of not h, but u, plus ke plus pe of a system that is not, of the part of the system that is not moving. And they don't really, I don't find the variable really quickly. So I think I'll just, yeah, it doesn't, I guess they just sort of eliminated that part of the discussion. So this will get you where you need to go. All right, so the basic idea then for problem solving, as I was saying, was to use the first law of thermo and the conservation of mass and eliminate terms as appropriate. So let's take a look at a couple of problems. Let's look at something that we can analyze as a steady flow problem and something that we can analyze as a uniform flow problem. So for steady flow, some of the main types of appliances that we're talking about are nozzles, diffusers, turbines. These are often, not always, but often, these are adiabatic. You need to check the problem and decide if that is a valid assumption or not. But if they are adiabatic, that means that Q is equal to Q dot, which is equal to 0 during the course of the operation.
No, what? Diffusers,
Often
turbines?
adiabatic,
No, yeah.
nozzles,
No.
diffusers, turbines. Okay. All right. So let's take a look. Let's take a look at 534. 534 is we have a nozzle, and here we are told it's adiabatic. All right. We're told that the working fluid is R134A. And what happens in this nozzle, we come into the nozzle at 700 kPa and 120 degrees centigrade. Right? Enters an adiabatic nozzle steadily with a velocity of 20 meters per second. And let's see, leaves at 400 kPa and a temperature of 30 degrees centigrade. Right? And it asks us the exit velocity. And it asks the ratio inlet, A in to A out. What does that equal? All right, so prior to this, this may seem like it was not a solvable equation, but now that we have some information about systems with flow through that are steady, we can address some of these questions. So since this is a steady flow, we definitely want to start with the equations for steady flow. And what do we know first? We know that the summation of masses on the inlet, mass flow rates on the inlet, have to equal the summation of masses on the outlet because, sure, because dm cv dt is equal to 0, right? Because in a nozzle, there's no reason to expect that mass would be entering or would be accumulating or discharging from the nozzle, right? Fills up and it just moves through, right? Now the other part we have for our first law equation, Q dot minus W dot equals the summation on the outlets, M dot times H plus V squared over 2 plus GZ minus M dot on the inlets, H plus V squared over 2 plus GZ. Because once again, we don't have any dmCv/dt, so we're not going to have any E rho dV changes either. All right, we're told it's adiabatic, so this goes to 0. What about work and power for a nozzle? Nozzles don't produce work or power, right? All they do is pass through and change the conditions of a fluid that moves through them. We also only have a single outlet, so we really don't have to worry too much about the summation sign. We also have a single inlet. We are going to have a change in enthalpy, or basically the flow energy of the material as it runs through the nozzle. We know that we have a change in velocities, but what about the change in potential energy? There's no real reason to expect that there's a change in potential energy from the inlet to the outlet, is there? Okay, so we have a simplified equation, and basically we start once again with the mass flow rate, and since we don't have a summation, we know that the mass flow rate in on the single inlet equals the mass flow rate out on the single outlet. And then for this equation, we also do not have, and let's just say it's equal to m dot, because it's the same. So in this equation, instead of separating it between m dot and m dot out and m dot in, I can just call it m dot. No summation sign, so I get 0 is equal to m dot times h plus v squared over 2 minus m dot, I should say this would be on the outlet, and this is on the outlet, m dot h on the inlet plus v squared over 2 on the inlet. All right, well, if it's equal to 0, I can bring that term over, and what's going to happen is my m dots, since they're the same, will cancel out. And so I get, as a simplified equation, h in plus v squared over 2, the velocity in, is equal to h on the outlet plus v squared over 2 on the outlet. All right, we're talking about R134A, so can we find H in the tables? Absolutely. We are told V on the inlet. So can we solve directly for V on the outlet on this equation? Absolutely. So I'm going to leave that to you guys to do that. But you can go table, table. V in is given. Solve for V out. Right? That is the first part of our problem. Now what about the area on the inlet compared to the area on the outlet? Let's talk about areas. Well, what do we know about a relationship between, let's just say, m dot and area? We know that q dot, or that, excuse me, we're calling it volumetric flow rate, wrong class, is equal to rho, which is the density of the fluid, times the velocity of the fluid. I'm sorry, this is going to be m dot. M dot equals rho V dot, so it's equal to rho V times A. So in our case, m dot on the inlet is the same as m dot on the outlet, which is equal to rho V, rho on the inlet, times V on the inlet, times the area of the inlet. And m on the outlet is rho on the outlet, times V on the outlet, times the area of the outlet. All right, and we know that those two things are equal to each other because mass flow rate remains unchanged. Now, the variable that we have is not rho, but we know in our tables, we know that rho is equal to 1 over little v, or specific volume, right? Okay, so we could rewrite this and say velocity on the inlet times area on the inlet divided by the specific volume on the inlet for R134A is equal to the velocity on the outlet, or the exit, times the area of the exit divided by specific volume on the exit. And since what we're looking for here is the area on the inlet divided by area on the outlet, we can rearrange this equation and say the area on the inlet over the area on the outlet, just dividing through by that, is equal to the velocity on the outlet times the little v on the inlet over velocity on the inlet, little v on the outlet, right? So algebraically, I can solve for that ratio as well. Any questions about that? Right, so this will be your first homework problem, 534. I've set it up for you. And then we're going to take a look at one. Sorry? Yeah, absolutely. Is that better? All righty. So another problem that we can look at that is, do I want to do that one? I'm going to look at a charging or discharging process, okay? And a charging or discharging process is generally going to have to be viewed in amounts, and it's going to have to be viewed as a uniform state. There may be parts of it that we can analyze using steady state, but most of it is going to be a uniform state because we have a period of time over which we can analyze the amounts that happen. So I'm going to look at problem 5-114, help you guys get it set up, and then once again that'll be your second homework problem. So 5-114, we have a 35-liter evacuated rigid bottle. Okay, when it says evacuated, that means that the mass at time 1 is equal to what, do you suppose? Yep. Okay. So it's the volume of this tank is 35 liters, which might require some conversions. and it is surrounded by atmosphere at 100 kPa and 22 degrees centigrade. The valve at the neck of the bottle is now opened, and the atmospheric air is allowed to flow into the bottle. So the mass at time 2, when you think about it, we said the mass at time 2 minus the mass at time 1. If we start from the beginning, the mass that goes in plus the mass at time 1 minus the mass that goes out is equal to the mass at time 2. Okay, there's no mass that goes out. There's no mass at time 1. So if we look at that, we can just say that the mass that enters the tank is equal to the mass at time 2, right? All the mass came from outside. The air trapped in the bottle eventually reaches thermal equilibrium with the atmosphere. Okay, that means this is at time 1. After air comes in, if it reaches thermal equilibrium, that means at time 2, the temperature at time 2 is 22 degrees centigrade, right? Valve is, okay, air is trapped in the bottle, reaches thermal equilibrium as a result of heat transfer through the wall of the bottle. All right, so that means that we have Q in or Q out. In other words, it's specifically telling you this is not adiabatic. The valve remains open during the process, so the trapped air also reaches mechanical equilibrium with the atmosphere. All right, mechanical equilibrium means that the pressure equalizes, which actually makes sense, doesn't it? If you're open to the atmosphere, the pressure and the temperature are both going to equalize. Determine the net heat transfer through the wall of the bottle during the filling process. Okay, well, we know what our mass flow rate equation looks like. And if we go back to a uniform flow problem, when we look at the amounts of energy, we start with this equation, and we find that Q minus W, okay, does this bottle change volume at all? So the W is 0, right, is equal to the mass, that we don't have any mass that goes out. The mass out term is 0. So we get minus, we have a single inlet of mass coming in, the mass in minus the H in, right? Plus the mass at time 2 times the U at time 2 minus mass 1 U1, which since there's no mass at time 1, that equals 0. So we have this equation. Now, the one thing that you need to remember is that since this is air, we're not going to have tables. So you may want to use a relationship, delta U du dt is equal to C sub P or C sub V. I can't remember which, but it's in your book. One or the other. And dH dt is equal to the other one. Okay. So if you find that equation, I believe it's in chapter 3, might be in chapter 4. You can then solve for delta U, and you can also solve for delta H. Okay, so you can make a supposition about Q based on that. Now the other thing that you might realize is that the mass at time 2 is equal to the mass that comes in, isn't it? So you could actually factor that out, and that would just be U2 minus Hn. Okay? And so you may get some more simplifying factors out of that equation. All right, do you guys have any questions? So your homework for tonight, for Thursday, is to finish both of these homework problems. And the numbers of our homework problems are 114 and 34. 534 and 5114. All right. And that is it for today, ladies and gentlemen. And please, I sent an email to you with a scholarship application for those of you that came in a little bit late. The scholarship application is due by the 7th of April, but it's a check that would be written directly to you from the NASA Space Grant in Laramie, so it does not interfere with your financial aid status at all. It won't figure into it, and you can still get money this semester. So apply, apply, apply. You guys have a great day.